Hi there, Andrew Dunkley here. Thanks for joining us on another edition of Space Nuts. Coming up this time, we are going to once again talk about the Ryugu asteroid. We've had a couple of discussions about it recently, but the news this time is not so positive, and it involves some kind of contamination that seems to have happened, despite everyone's best efforts to avoid it. There's also a new theory that's been put forward, thanks to computer modelling, about how the moons of Mars may well have formed. There's a few theories. This is a new one to add to the sphere. Boom, boom. And the first results from a new instrument on the William Herschel Telescope. We'll talk about all of that on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining me to talk about all of that and much, much more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see you.
Good to see you too. Now, before we start, I'm going to put you on the spot because I've been looking at the calendar and working a few things out. This episode will be officially released on the 12th of the 12th, and your birthday is 2 days later, and you're turning 800. No, hang on, it's got an 8 in it.
Yeah, but it begins with an E, and it's not 11, so that's a clue.
So I suppose this episode we should start by collectively wishing you a very happy birthday, Fred.
Thank you very much.
It'll be 2 days' time after the release of this episode, even though we're recording this one in 2021. So,
speaking for yourself, I thought it was 1947.
Yeah, it could have been too. No, we're running a bit early to see out the year, but I hope you have a wonderful birthday, Fred, and many, many more.
Yeah, that's the important bit.
That is the important bit.
Yes, that's right.
Got to keep this thing, the brain cells ticking over. I think that's the secret to long life.
And I think Space Nuts.
Keep the brain working.
Space Nuts.
Yes, absolutely. Now, we have got some fascinating stories today, and we'll start off with Ryugu, the asteroid that was visited, a Japanese mission, I believe, that brought back samples, and they've been looking at those samples, and now they've looked at them and gone, oh, hang on a minute, what's happened here? Somebody spilled some jam on them or something. No, it wasn't that, but they do appear to have become questionable in terms of their quality, because the effort to keep them clean has failed.
That's right, and that's really the lesson of this story, just how hard it is to keep earthly microbes away from anything. And, it has implications with our sterilisation processes for spacecraft going to other worlds. We've talked before about the planetary protection rules, which mean that if you're sending a spacecraft to somewhere on Mars where liquid water could exist, it's got to have the very highest, if I remember, it's category 4C sterilisation, which means that there are only 30 microbes on board the spacecraft. I don't know how they do that, but that's what they do. But what this story is telling us is that might not be enough. That might just be effectively scratching the surface. And so this is some work that's been done at Imperial College in London, one of the London universities, and a paper that's been published in Meteoritics and Planetary Science, which is called Rapid Colonization of a Space-Returned Ryugu Sample by Terrestrial Microorganisms. And basically, it tells you that on the surface of the samples that came back to Earth it's via the Hayabusa 2 spacecraft from Ryugu, they have found microbes, basically. And it's extraordinary that, despite everybody's best efforts to keep these free from contaminations, they've got contaminated. I might just read a very nice article on phys.org, which is it's one by Justin Jackson. And there's a paragraph here that tells you what basically what the samples underwent to keep them clean. So I'll read that. Transported to Earth in a hermetically sealed chamber, the sample was opened in nitrogen in a class 10,000 clean room. I don't know what that means, but it sounds very clean, to prevent contamination. Individual particles were picked with sterilized tools and stored under nitrogen in airtight containers. Before analysis, the sample underwent nano X-ray computed tomography and was embedded in an epoxy resin block for scanning electron microscopy. But they found these what are described as rods and filaments of organic matter. And a lovely phrase here, interpreted as filamentous microorganisms. Were observed on the sample surface. Variations in size and morphology or shape of these structures resembled known terrestrial microbes, and observations showed that the abundance of these filaments changed over time, suggesting the growth and decline of a population. It's incredible, isn't it, that no matter what you do, you can't keep them clean. And so it's really a lesson, I think, for our future understanding of the exploration of life beyond the Earth. For a start, it means that there's probably microbial contamination now on Mars, on the Moon, all over the place.
If we've created a really significant clean environment for those samples we brought back, it stands to reason we've sent microbes to other worlds, because we probably weren't that thorough in sending those spacecraft. And if the safety situation was so strict on the Ryugu samples and the microbes got through, it stands to reason that we have sent microbes all over the solar system.
Yeah, pretty well everywhere.
It's a bit scary, really, because if there is a world with life and we've sent microbes to them, what could happen? I mean, my logic says to me our microbes wouldn't survive, but they're pretty tough.
And more than that, they adapt. There's another lovely paragraph from Justin's piece on phys.org, which is basically what we've just been saying. NASA tries to avoid introducing Earth microbes to Mars by constructing probes and landers in cleanroom environments, and has found the task nearly impossible. There have been species of microbes, wait for this, there have been species of microbes discovered in NASA cleanrooms that not only evade disinfection methods, but also adapt to using cleaning agents as a food source.
Yes, I know. That absolutely blew my mind when I read that. Good grief.
I know, yeah.
So, I mean, that is a glaring example of adaptation to an environment, isn't it? When
that's right.
After the week, let's eat the petrol.
Yes, exactly. Yeah, that's basically what they're doing.
Quite incredible.
That's quite.
Now, I know that somebody in our audience, probably more than one person, will say, "Hang on a minute. How do we know that these weren't microbes that already existed on Ryugu?" And they're pretty positive that they aren't. The article says population statistics indicate that the microorganisms originated from terrestrial contamination during the sample preparation stage, rather than being indigenous to the asteroid. So, they are very confident and probably disappointed that they are not.
Yeah, that's right.
Asteroidal origin.
Yeah. I mean, people do look for signs of perhaps fossilized microbes in meteorites, particularly. And you'll remember it's ALH 840001, I think was the name of it, the Allen Hills meteorite, which in the early 1990s was found to have, within its structure, these weren't on the surface like these things that have been found in this story, but within its structure, it was found to have things that strongly resembled terrestrial microbes. only they were about 1,000 times smaller. So they started calling them nanobes. Because they were a lot of nanoscale rather than microscale. But it turned out that there are simple chemical reactions that take place in geological formations that can produce these things that look like living organisms. So the astrobiology community has been pretty strict about what the criteria are for having discovered life in a meteorite. And it's not just that you find something that looks like a microbe. I think there are chemical tests and things of that sort that will be done that would, verify if this was indeed a microbe that had come from Mars. I think, it's still possible we might find something like that. I think there's so much activity in this field, Andrew, that I think there's a good chance we might one day turn up a Martian microbe. And even more likely, that when finally the soil and rock samples from Perseverance come back to Earth, that we might find something in there. That will be the really exciting story when NASA and ESA get their act together. I don't know what the situation is, but I think it's still in abeyance because everything that they planned was going to cost too much. But to bring back these little tubes of Martian soil and rock that have been left by Perseverance on the surface of Mars.
Yeah, that's so human, isn't it? Let's get some samples. Yeah, but what are we going to do about collecting them? Oh, yeah, we'll figure that out. We'll figure it out later. Oh, hang on, it's going to cost too much. Oh, well, we'll figure it out much later.
Well, that's basically where we are now. Yes. Unless there's other developments I'm not aware of. Yes, it's a very human thing. She'll be right.
But I do agree with you that sometime in the not too distant future, we will find evidence of past life somewhere in the solar system.
Really?
And this is a classic example of how life can grasp even the smallest, almost impossible opportunity.
Yeah,
and
that's right.
If that can happen in a room that's designed not to allow it to happen, then it could probably happen anywhere.
Exactly.
And you don't even have to add the caveat if the circumstances are right, because the circumstances were not right, and it still happened.
Yeah, that's right.
Quite extraordinary. Yeah. Amazing story, and you can read it at phys.org. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson.
Roger, you're allowed to clear here also.
Space Nuts.
Now, this next story takes us to Mars, and there's a new theory that's been put forward about the origin of the moons Phobos and Deimos. I think there were two theories that previously existed, and that was that they are both captured asteroids. I think the other theory was that something hit Mars just like Theia hit Earth and created the moons as a consequence of that impact. Now they've got another idea, and this one seems to have just as much validity, maybe more.
Yes, that's right. In fact, it's the modelling really seems to demonstrate that this is on the right track. It's a study that's been carried out by scientists in the United States, as well as using some code that Durham University has prepared. That's the University of Durham in the UK. They've got one of the most advanced computing systems in the United Kingdom, and they've used it to build models of the universe that are kind of complete in every detail. It's amazing stuff. So that computing facility has been used in this research, trying to work out what happened to create these two tiny moons of Mars, Phobos, which, if I remember rightly, is about 23 kilometers across, shaped like a potato, and Deimos, which is quite a bit smaller. I think it's only 15 or thereabouts kilometers across, and shaped a bit like a smaller potato. So you're quite right. Two theories are, one is that they were simply asteroids that were captured when they passed close to Mars, and the other one is that perhaps there was a giant impact, exactly as you've said, a little bit like Theia impacting the Earth and creating the moon, an impact on the Martian surface that lifted an enormous amount of material to form a disk of material around Mars, and the moons are basically formed in that disk. And that's probably the more popular theory. But that the reason for that is that it really neatly accounts for the orbits of Phobos and Deimos. That's why people like that, because it sort of matches the present day orbits of Phobos and Deimos. That's what you get if this ejector from an impact had collected in orbit around Mars. But there is a snag, and one is that if that had been the case, if these worlds are made of material that was ejected from Mars itself, they would have formed closer to Mars than they are. And there's a gotcha, in particular with Deimos. It's the radius of its orbit tells you that it actually had to form that far away from Mars. It couldn't have formed very close to Mars and then migrated outwards. It would have basically just gone back to Mars and crashed again. And so this new material, this new model suggests that the material from which these two worlds are made, Phobos and Deimos, didn't come from Mars, that it came from an asteroid that passed too close to Mars's surface and basically broke up as it bypassed Mars. So if you imagine an asteroid heading in Mars's direction, it's not going to impact the planet, but it's going to do a near miss. Now, a near miss means that it's very close to Mars's surface and it feels very strong tidal effects. And what we mean by tidal effects is the difference in the gravitational pull on one side of an object compared with the other. That's what creates tides on Earth. So the near side of this asteroid, the hypothetical asteroid, would have felt more gravity than the far side. And that creates tension within it, which basically breaks it up. So this thing cannot withstand the tidal forces. It breaks up into debris and then circulates around Mars, and eventually Phobos and Deimos are formed within that ring of material. In fact, it very nicely accounts for the differences between Phobos and Deimos and the different orbits that they've got.
Okay. Well, so it's not dissimilar to theory two that what they're saying, to expand on what you were said. It's an asteroid that was passing Mars. The gravitational effect caused it to break up. But further to that, all those bits and pieces continued to collide and smash up and created a protoplanetary disk, if you like.
Yeah. Yep.
On a Mars scale, and then that formed into the two moons. Is that that's what they're saying?
That's correct. Yes, that's what they're saying. And and the model sort of makes predictions about the orbits of the final orbits of the moon, which basically are what we see in reality. So yes, it's a very nice piece of work, and there is some possibility that we might get some hard and fast results from both Phobos and Deimos, because there's a JAXA spacecraft, Japanese Aerospace Exploration Agency, called MMX, which is the Martian Moons Explorer, or Martian Moons Exploration Mission. And it's a sample return mission. And of course, the Japanese are very good at sample return. We've just been talking about the fragments of asteroid Ryugu, which is a sample return from an asteroid. So this mission will bring back samples from both Phobos and Deimos and give us a lot more close-up studies of those two worlds. And so, we might find from whatever they bring back that we find the compositions of the moons actually would match what this scenario suggests, because you'd expect if it was a broken-up asteroid, you'd expect the material, the isotopic content of the material of which Phobos and Deimos were made, would match that of the asteroid rather than Mars itself. which is what you get from a collision. So MMX launch in 2026, and something I hope we'll talk about on the Space Nuts.
Absolutely, yeah. One question though, if that was the case, and you can write off theory one, which was Mars just captured 2 passing asteroids. Theory 2 and theory 3 still see ejector or material being used to form the moons. Why wouldn't they be spherical if that's the case? Big enough for the gravity to create them.
Yes, that's correct. That's absolutely it. So it's like a lot of asteroids are wobbly shape. They're a bit like some of them are very like spinning tops. They're the rubble piles. Some of them are like potatoes. Some are like dumbbells, and that's probably 2 asteroids that have come together, they're originally in orbit around each other and have now become one. So a sample return would, I think, allow a distinction between all of those models. So we might have a very good model in much the same way as sample returns from the moon back in the 1960s and 70s gave us our ideas for how the moon formed.
Okay. Yeah, you know what we've learnt from this from a horticultural perspective, Fred? If potatoes on Earth grew bigger, they'd ultimately become spherical. That's what we've learned from this.
They would. They absolutely would, yes, a spherical potato. But they'd have to be big enough for their own gravity to pull them into a spherical shape while they were in free fall. So you need to be throwing them up in the air as well as letting them grow bigger.
That would just add to the price.
Yeah, they'd have to get up to in the region of 500 kilometers in diameter, and most potatoes are not actually. You see these prize-winning marrows and pumpkins and things like that people need a wheelbarrow to move around with. Forget it, spherical potato.
It's an interesting hobby, that, and I just don't understand the logic of growing giant fruit that nobody can eat or giant vegetables.
So, you can turn them into motorway crash barriers and things like that. They're quite useful in that regard, but
Yes, you can. Oh, gosh. It's a really interesting theory, and it probably holds water compared to the other 2. Theory 2, theory 3, both same end result, different techniques.
That's right.
Yeah. But you can read that story at nasaspaceflight.com. This is Space Nuts. Andrew Dunkley here with Professor Fred.
0G, and I feel fine.
Space Nuts.
Our final story, Fred, looks at an instrument. It's not a violin, a cello, or a saxophone. It is an instrument connected to the William Herschel Telescope, and it's just come up with some really interesting information about colliding galaxies. Do tell.
Yeah, so just about the instrument itself, which is something built by very close colleagues of mine, actually, at the University of Oxford in the United Kingdom. And it's a little bit like, we have a thing called 2DF on the Anglo-Australian Telescope. 2DF stands for the 2-degree field, and it's a device that lets you position optical fibers, and in fact, in 2DF there are 400 of them, in exact alignment with the images that the telescope delivers. So you can, for example, measure the characteristics of 400 stars at a time or 400 galaxies at a time. And, back in the day when I started my career, you could only observe the spectra, the rainbow spectra with all its information locked up in it. You can only do that one at a time, at least to get the details. So
you and I did a little TV special about the 2DF when it was installed. Yeah.
Yep.
I remember that.
That's right. So 2DF has been incredibly successful. Now, the William Herschel Telescope, which was built, if I remember rightly, it was commissioned in 1987. It's a telescope of a similar size to our Anglo-Australian telescope. It's got a slightly bigger mirror. It's 4.2 meters as against 3.9 meters, but it was built by the same company, Sir Howard Grubb Parsons, with whom I started my career, Andrew. And so the William Herschel Telescope is not in Australia, though, like ours is. It's on the island of La Palma, which is one of the Canary Islands off the west coast of Africa. And La Palma is basically a giant volcanic cone. In fact, it has an active volcano in the south of the island, which has been in the news within the last couple of years.
I think Judy and I will be visiting there next year.
Oh, well.
I'll have to check our itinerary, but I've got a feeling we do make a stop at the Canary Islands.
Yeah, well, there are quite a few Canary Islands, but La Palma is certainly the interesting one from an astronomical point of view, as is Tenerife, the bigger island not very far away. That's got telescopes on its summit, a mountain called Teide. The mountain on La Palma is El Roque de los Muchachos, which means the Rock of the Brothers or the Rock of the Friends. It's the sort of strange rock formation on top of the mountain. But that's where the telescopes are, including the William Herschel Telescope, which for a while was the biggest on the island at 4.2 meters. There's now a 10-meter telescope called Telescopio Grande, TGC, Telescopio Grande Canarias. It's a Spanish telescope with a 10-meter mirror. And that's...
You know why they call it that? Gives you a bird's eye view.
Canary Eye view, of course. That's right. Yeah.
Yes.
You know why the Canary Islands are called the Canary Islands? Here's a friendly factoid.
I don't know, actually. I've never looked it up.
Right. Well, it's not because of canaries. It comes from the Latin word canis for dog, and it's because there were dogs on the island. So it's the dog island, basically.
Wow.
Because Canis Major, the great dog in the sky, the Canary Islands had dogs on them. That's why they got called that. By the Romans, I think, which is why it's Latin. Anyway, enough of that. So what's this telescope got that we haven't got? It's now got something called WEAVE, which is the William Herschel Telescope Enhanced Area Velocity Explorer, which is a similar system with a slightly different methodology for positioning optical fibers. And as I said, it's very good friends of mine who've been involved with that. And one of them is actually quoted in the article I was looking at, Professor Gavin Dalton. I might just tell, I hope you're not listening, Gavin, because I'm going to drop you in with a very well-known story. Gavin was one of the commissioning scientists with 2DF, did a lot of work on the actually with the 2DF survey, a lot of work on the telescope. And he was one of the first among us to have a MacBook, which, of course, comes with a power supply. One epic night, at the start of the night's work, Gavin plugged his power supply for his MacBook in one of the wall sockets in the control room of the Brazilian telescope, and there was a bang, and we lost all power for the night. Yeah, I don't know quite what happened with that, but Gavin was very embarrassed about it. I think we eventually got going again. I was there at the time, but it was quite everything just died, including this. Yeah, well,
I can understand that. We had that happen at a radio station once because a cleaner plugged the vacuum into a UPS socket.
Okay. Yes.
And the whole place just went dark because
through too much.
Just, wow, yeah, it killed everything.
Well, it may have been something like that with that MacBook thing. So, yeah, good old Gavin, he's done a fantastic job, a great scientist, working with Ian Lewis, another friend and colleague at Oxford. Ian was actually out for our 50th birthday celebration on the Anglo-Australian Telescope last month. Anyway, that's the instrument and all I know about it. What's the story? Well, it's been used in its commissioning mode. They're sort of just, finishing it off and making sure everything works. They have used it to explore some of the galaxies in an area of sky beloved to astronomers called Stephan's Quintet. And Stephan's Quintet is a quintet of galaxies very close together. One of them actually is not part of the group physically because it's about half the distance of the rest. The rest of them are a physical group which are interacting. These are four galaxies very close to each other, which are themselves, pulling each other about because of their gravity. And it turns out that by using the WEAVE instrument to look at the velocities of material that are basically being carried by the shock waves of the collision, they've explored this and are quite amazed by the sorts of speed that are being reached by these essentially these shockwaves of galaxies. So one of the collision speeds is 3.2 million kilometers per hour, which is quite fast. That's two of the galaxies colliding. And so the shock wave between them, because they've both got gas clouds around them, there's a shock wave formed by this collision. And that is basically, causing other things to move around. And you can explore that movement by something called the Weave Large Integral Field Unit, or LIFU, which is a way of putting many, many optical fibers on galaxies so that you sample the movement of objects in each galaxy. You create what's called spactals because it's a three-dimensional pixel, if I can put it that way. So you've got velocity in one direction and basically the image in the other. So this work's come now from Weave. It looks like a very, very high impact result. And in fact, I can quote the director of the Isaac Newton Group of Telescopes on La Palma, Mark, I'm not sure how you pronounce his name because he's not somebody I know, Balcells, I guess, who says, "I'm excited to see that the data gathered at the Weave First Light already provide a high impact result. And I'm sure this is just an early example of the types of discoveries that will be made possible with Weave on the William Herschel Telescope in the coming years."
Yeah, great. That's extraordinary. Does that suggest that similar things could happen with Andromeda and the Milky Way colliding? Wouldn't it? Yeah,
it does. Let's see. We've got similar collision speeds. It's about 200 kilometers per second, if I remember rightly, that we're approaching Andromeda. What's that multiplied by 3,600? It's a lot. And so about 300,000, isn't it? Yeah, 600,000 kilometers per hour, which is getting on for 1 million. So the speeds are not quite as big as what we're seeing in Stephan's quintet, but they are nevertheless big enough to cause shock waves. And that's what will lead to star formation. It'll cause stars to form rapidly, and we might get many supernova explosions, which might be the most obvious consequence of the Andromeda Milky Way collision when we see it in 3.2 billion years. Watch this space nuts.
It's on my calendar. Yeah, good. No worries. That's a great story. So you can read all about that. Julie's here. He's excited, very excited. Phys.org. Phys.org is the website. Lots of great stories there. It's a fabulous website. Really love it. And that brings us to the end of the program. Don't forget to visit us online at our website, spacenutspodcast.com or spacenuts.io, and have a bit of a browse around. If you're looking for Christmas gifts, well, we've got a shop. So if you've got someone that, you just can't think of anything, but they like astronomy, the Space Nuts shop is the place to go. And plenty of other things to see and do while you're there. Fred, thank you so much. Great to see you. Thanks for filling us in on all of those great stories today.
Sounds good. Thanks, Andrew, and we'll talk again soon.
We will indeed. Professor Fred Watson, astronomer at large, and Hugh in the studio. Well, Hugh couldn't be here today due to a microbial contamination. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.